So won't be unemployed for too long, hopefully. Okay, so we're asked to start with a very broad introduction. So non-commuting charges, what are they, and why should you care? Well, across physics, systems exchange quantities. So typically, you first encounter this in the context, maybe an undergraduate stat mech of some system interacting with an environment. It's exchanging some quantity Q1 and another Q2. These quantities are called charges if they're conserved globally. That's just the name for them. Now, an implicit assumption, it's so implicit, you might not have realized it was there. So we assume charges commute. So for example, this assumption underlies derivations of the thermal states form, transport coefficients. These are things like the Onsager relations, like things like the Seebeck effect, the Peltier effect, Fick's law, Fourier's law. It also understands the eigenstate thermalization hypothesis. So it's one way in which we can understand how reversible unitary dynamics can lead to thermalization. So in short, it's under a lot of things. But we know that charges may not commute. And in fact, charges non-commutation plays a particularly important role in quantum mechanics. So for example, it underlies uncertainty relations. So we're really compelled to lift this assumption and ask, well, what changes if charges don't commute? And I think this picture really summarizes it well. So if you ever play Jenga, here's one tower we're trying to remove, and that tower, there's the assumption that charges commute. And built upon it are many different derivations from quantum information thermodynamics. And this is about what happens. And so people have been patiently rebuilding this tower, and as they go, discovering new physics on the way. And so we have this review article here that outlines many of the different results. I'll just mention a couple that motivate some of the questions I'm interested in right now. So one is this work by Gabriel Landi and collaborators. I mentioned Gabriel because he'll be here later this week. And so they look at the rate of entry production in a collisional model, and they consider a case where you have commuting and non-commuting charges. And both analytically and numerically, they find that the model with the non-commuting charges decreases the entropy production per collision. There's also this other work that looks, I'll call it an anomalous deviation from the thermal state. So okay, I should explain what there's this thing called the eigenstate thermalization hypothesis, or ETH. And it's a statement about an observable and a Hamiltonian. And if they obey the ETH, the time average expectation value of the observable will equal the thermal expectation value plus some correction. So, and this is a way to understand how unitary dynamics can lead to thermalization. Under reasonable assumptions, if you have non-commuting charges, that deviation can be larger. So the reason I mentioned these two results is they tell a bit of a similar story. Reducing entropy production, getting further from the thermal state, they suggest some kind of hindrance to thermalization. And that fundamentally, I think that's very interesting if there are certain types of symmetries that resist thermalization. But also maybe there's some type of practical application down the road we could find for it. Maybe things like, if we can resist thermalization, maybe we could leverage that for better quantum batteries or quantum memories, let's say. Usually at this point, I'm asked for a physical example, and the simplest thing is just a Heisenberg chain. So here you could have 6 qubits. We have the Heisenberg interaction, so quanta of spin are hopping between sites. Our 3 non-commuting charges are the 3 components of the spin, and each are conserved and they don't commute with one another. An initial experimental testing of non-commuting charge physics has begun. So this is an experimental work that was done in Rainer Blatt and Christian Musa's group, looking at the thermalization of systems with non-commuting charges. So this is some reasons why we think non-commuting charges hinder thermalization. What really makes this story interesting is that there's also results suggesting non-commuting charges may promote thermalization. So, to thermalize or not. One of these results is the effects of non-commuting charges on entanglements. So entanglement is obviously interesting for many reasons. One is that it accompanies thermalization. So that ETH picture I described leans heavily on the entanglement. And it's interesting for many other reasons, signature of chaos, it's resource computing, at least We start with pure states. And so we want to ask the question, what's the effects of non-commuting charges on entanglements? But the problem is non-commuting charges, I mean, non-commutation isn't a switch you just flip on and off. So you're really comparing apples with apples if you make such a comparison. So in this earlier work, we constructed analogous models that differ in whether their charges commute, and found that the non-commuting model has more entanglement on average. So this is an earlier work that I won't have time to get into today, but that's the story of it. And so this suggests maybe a promotion of thermalization. Following up on that, so we looked at the entanglement in terms of page curves, which paints a somewhat static picture of entanglement. We're interested in the dynamics of entanglement. Can we look at circuits that entanglement is growing and see, okay, what's the effect of non-commuting charges in this setting? A really useful and very interesting toolbox. Yeah, maybe I shouldn't say useful. Maybe whether or not it's useful is to be determined. But a very interesting toolbox are monitored quantum circuits. And they're useful for understanding universal properties. So you can introduce, you start with a very minimal model, and you can introduce something like the symmetry and say, okay, how does that change the dynamics? This is going to be the main focus of my talk today, so I won't say too much right now. But in short, in this setting, we find a critical phase, and it replaces the less entangled phase. So you can have a similar consistent story of non-commuting charges seeming to promote entanglements. But I'll talk about this more. And I had to mention something more directly about thermalization because I'm motivating a discussion on entanglement by connecting it to thermalization. So I should at least mention a little bit of the epilogue and what came after. And so we asked the question in a follow-up work, well, one way to approach this problem is to say, okay, most systems thermalize. Actually, not thermalizing is quite unusual. Well, let's go through the cases that don't thermalize and see what happens if we force non-commuting charges into that setup. And an earlier work had done this with, so maybe for the expert audience, with studying MBL, they introduced non-commuting charges into MBL and found they destabilized the MBL phase. But in a similar spirit, let's look at a type of system that doesn't thermalize. And here it's a Hamiltonian with a dynamical symmetry. What is a dynamical symmetry? You have some operator. It could thermalize. Dynamical symmetries are structures of the Hamiltonian that stop that operator from thermalizing. They're, for those familiar with spectrum generating algebras, they're similar, but they're local. And we find that non-commuting charges eliminate dynamical symmetries as well. So it's another type of non-thermalizing behavior that non-commuting charges are getting in the way of. So I'm going to focus, and animation. So we're going to focus on this middle work here, but this is kind of where it fits in on this larger picture of what we're studying right now, trying to resolve this puzzle and understand how non-commuting charges really affect thermalization. Okay, so monitoring quantum circuits, these are probably one of my favorite things to play with. I'll just walk you through what they look like. So you start with L qubits in some initial state, rho I. System is evolving in time. And then throughout the circuit, you disperse random unitaries laid out in a brickwork fashion. So they're staggered like so. And the unitaries are trying to entangle your qubits. Between each layer, you have projective measurements that occur with some probability P. So if P was 0, there'd be no blue dots. If P is 1, there'd be blue dots at every point. And the measurements are trying to disentangle. So you have this nice tension here between trying to entangle and trying to disentangle your circuit. You get to some final states, and you can measure the bipartite entanglement entropy of the system. So you cut the system in half, and you see how entangled it is. The reason this quantity is interesting to look at is because it reveals a phase transition. So you're not measuring often enough. The unitaries essentially win the battle of entangling versus disentangling, and your circuit evolves to a highly entangled state. So it enters a volume law phase, where the entanglement grows as the volume of the system. So for a 1D chain, that's L. In the area law phase, when P is above the critical probability, you get entanglement that grows as the area between the two regions, which is a constant for a 1D chain. And at the critical point, you have log L scaling. These circuits are interesting for various reasons, one of which is that this entanglement transition can be equivalently viewed as a purification phase transition. And in this case, you can imagine you start initially with a mixed state and you evolve the circuit. The measurements will eventually evolve you to a pure state. You can ask the question, how long does it take to get to that pure state? The volume law phase corresponds with a mixed phase, where it takes an exponentially long time to purify. In the area law phase, it's again constant. At the critical point, we have the scale invariant behavior of purification time going is L. Which really is a good point to pause. Is there anything you can clarify about, when we get into new stuff now, about monitored quantum circuits or non-commuting charges? No? Okay, feel free to ask later. So people have added many different things to monitor quantum circuits, one of which is charges. When you do so, you can find a second type of phase transition. So the charge here is the total spin along the z-axis. So you can just think of that as the number of ones or zeros in your initial state, so number of ones. You have your gates and measurements conserve this value. What you find is a charge sharpening phase transition, where if you're measuring fast enough, so essentially what you're doing is you have your circuit, you start with an initial number of ones, let's say, and you're doing local measurements asking how many ones are there. In one phase, you're measuring fast enough that you can determine the global charge from these local measurements. In the other phase, you're not measuring fast enough and the information gets scrambled before you can determine the global state. Now they close this paper with a really interesting question of, well, amongst other things, a question of what if the charges are non-commuting? One natural question is, can you even learn the charge? Because later measurements are going to partially interfere with the earlier measurements. And another is, do the entanglement dynamics change? So in the symmetry-free case, the U1 case, and others people have studied, there's this volume law, a critical point, and an area law. If we suppose for some reason non-commuting charges are increasing entanglement in some meaningful way, maybe we should expect to see it in this diagram. And so that's what we set out to do. So our setup is an SU2 symmetric monitored circuit. So you take your usual circuit, you now have three charges that are non-commuting, the total spin along each axis, or you can write them as a sum over Pauli matrices. And you restrict your unitaries and projection operators to conserve these charges. The most general unitary up to a phase has this form here. And to define the projection operators, we first define the singlet and triplet states. And we get our projection operators are the rank 1 projection to the singlet and the rank 3 onto the triplet. So we take our symmetry-free circuit, change the unitaries to be SU2 symmetric, change the measurements to our new measurements that now necessarily act on two sites. And then instead of doing the unitary followed immediately by the measurement, we'll just do the measurement. This is our object of study. What do we find? Well, first we find a critical phase. There's actually that less entangled area law phase no longer exists. You can't get to it with any amount of measurements. We also find a spin sharpening transition. Time permitting, I'll talk about that. If not, I'll just say why it's interesting. So how do we know it's a critical phase? Well, the first piece of evidence, the first thing we're looking for is scale invariance. Okay, so briefly, what do I mean? So you have some function of L, so it's the number of qubits in your system. You scale L by some amount, and you're going to get back your original function up to a scaling that looks like that. So for example, power laws have this property. So we want to measure the purification time of our circuit. So how do we do that? We're starting with a mixed state. We want to eventually know when it purifies, how quickly is it purifying. That might seem complicated. One way to do it is to take two eigenstates from the same charge sector that are orthogonal to one another. You're going to start with that state, and you're going to entangle those with an ancilla. So you start with this initial setup. If I measure the entanglement entropy of the ancilla right away, before I start the circuit, it's going to be at its maximum value. If I run the circuit, as the circuit purifies, so too will the ancilla. And if I measure its entanglement entropy, it's going to go to 0. So by tracking the entanglement entropy of one ancilla, I can measure the purification time of the circuit. That's what I do there. And then so the purification time is a function that goes like this, and we fit numerics to estimate it. So this is an example of what one of these plots would look like. So here I have my measurement rate is 0.05, so it's very small. And here I have the entanglement entropy is of the ancilla plotted against time. Here's divided by L squared. Why L squared? You can take that as my guess for what the purification time is in this phase. These lines didn't collapse, so I guessed wrong. We can do this though from different values of P. What we find is they eventually do collapse, and they stay collapsed. In the symmetry-free U1 pictures, what you have is this, you start with this fanning out, it collapses and it fans the other way, and it collapses at the critical points. So here the curves collapse, we have a phase transition, and they collapse to an L squared, a scale invariant phase, so it's power law, so it's some kind of critical phase. Now from the first talk this morning, this might look familiar, we have the dynamical critical exponent of z equals 2. So maybe you could think, okay, maybe this is some kind of diffusive Magnon type story. Understanding this analytically is still an open question. The next thing we would look for is large mutual information. So if we take our chain of qubits, we then connect them at either end with periodic boundary conditions. We can look at the mutual information between opposite ends of the chain. At a critical point, the mutual information would rise as we approach the point, it would peak, and then it would drop back down. For critical phase, it should peak and then stay large. And so that's what this plot here is showing. We have the mutual information for different values of P. As we increase P, the mutual information increases. And as P continues to increase, it continues to go up, it doesn't go back down. So large mutual information. And then finally, we're looking at the entanglement growth of the system. So we can plot the entanglement entropy against the system size. And you can see from this picture that there doesn't seem to be an area law, that it's growing with L. So clearly no area law phase. We can try to fit in the different values of P, but we're essentially just limited by the system size to get good fits here. So even at P equals 0, I mean, clearly the volume law fit's very good, but really the log L fit isn't like awful. So you can at least say the numerics are consistent with volume law. And as you go to higher values of P, I mean, the most that we can fairly say is the numerics are consistent with log L. And we transition from volume law to log law. Actually, a recent paper just came out that studied this model further, and they have an analytic argument for why it should be log L. So pretty confident with that piece as well. So I guess maybe two things to point out here. One is a natural question of, okay, why stop at 20 qubits if that's like a limiting factor to your good fit? Well, we're doing SU2 symmetries, so we can't do Clifford numerics, just be trivial then. And we're also doing a transition from a volume law to this critical phase, so we have this very highly entangled initial phase, so tensor network techniques become difficult too. So this is all with exact diagonalization. I mean, like one of these points, we use Compute Canada's high performance computing cluster. I think it was like 21 years of computational time. So taxpayer money well spent to make this plot. But that's why we stopped at 20. And you might ask, okay, well, there's two measurements. Is that the reason you're getting more entanglements? So in short, no. People have done two-site measurement monitored quantum circuits before, and you still have the high entangled phase and the low entangled phase. You still get the phase transition from volume to area law. And the measurements are only creating entanglement with one other qubit. Okay, so to recap, I mean, originally we had the symmetry-free, the U1 cases, and other monitored quantum circuits from before. We had the SU2 symmetry, and we have the usual volume law phase. We transition to a phase with purification time is L squared. Numerics are consistent with log L, and large mutual information indicating a critical phase. So again, the story is suggestive that non-commuting charges seem to be restricting our system to more entangled states. Okay, I don't have time for spin sharpening, but let me just broadly say what it is. So imagine I'm running through my circuit, and right now I'm in this extreme case of measurement-only dynamics. I do a measurement, I measure a singlet and a triplet. I then go to the next stage, and now at the next level of measurements, I could measure a triplet with one probability and a singlet with another. Probabilities are here. Then I go to the subsequent measurement step, and I no longer am guaranteed to get the state I started with. Like the measurements we're gaining information, but they're rendering some of the early information partially irrelevant. So the question could be, do you even get a transition in how efficiently you can measure the charge? I'll skip that. And in short, we do. It's a phase transition that corresponds with our entanglement transition. In one phase, it takes an L cubed amount of time, in one, it takes an L squared. Yeah, so it's my brief recap of the spin sharpening. So I want to fit this into the bigger picture, the bigger puzzle that we're trying to resolve here. So to recap, we hinder thermalization. Reasons to believe that is the reduction in entropy production, the anomalous deviation that I mentioned. There's also interesting work where you can ask the question, say I want to do some global unitary, and I want to do it from unitaries on two sites. So in the symmetry-free case, you get anything you want. You know, from any, you can build any global unitary from two-site unitaries. But now let's say you want to add the restriction that your local unitaries are U1 symmetric. Can you get any U1 symmetric global unitary? The answer is no. And that restriction becomes even more severe if you have a non-abelian symmetry. So that was this work. And there's two derivations of the thermal states form that are invalidated from non-commuting charges. On the other hand, we've seen the increased entanglement we talked about today. There's also the blocking of various forms of non-thermalizing dynamics. So there's many-body localization, this follow-up work with dynamical symmetries, another work related to quantum scars. And I guess in this paper, we argue why this paper's results mean non-commuting charges block quantum scars. Okay, so in this work, we find that we induced critical dynamics in monomer quantum circuits. We found a critical phase and discovered a spin sharpening transition. Where do we go from here? I think it'd be very interesting to resolve the thermalization puzzle, understand the effect of these charges on that. It'd be interesting to understand the critical phase analytically. So with a dynamical exponent, it seems like something diffusive is happening. What is it exactly? Can we get a nice analytic model for that? And I think an interesting problem would be to see if there's any kind of way that we can kind of spoof the non-commuting charge results with some combination of commuting charges. Is there any combination of abelian symmetries we can create that would make it seem like we get a similar result as what we did in the SU2 case? And then, I mean, this might be a bit more technical, but when studying monomer quantum circuits, there's something called the post-selection problem, which comes from needing to have the same measurement outcomes in multiple trials of the experiment. And so with the spin sharpening transition, it gives us a way to overcome the post-selection problem in part, because we can instead just ask the question of, can you determine the spin within a certain time period? If yes, you're in the one phase. If no, you're in the other phase. And the exact measurement outcomes aren't what's important anymore. Okay, thanks for listening. I want to thank my collaborators. I want to preemptively apologize if you see me run out in the middle of the talk. That's because of my upcoming collaboration with my wife. The project is due sometime this week. So I usually say it's going to be on the archive soon, but he will not be on the archive. And then, yeah, and it's my privilege and also contractual obligation to mention I have a book. It's already out. You can buy it. It reviews how different types of quantum computing hardware are built. And actually, I mean, connection to the Bell Prize at John Prestel. They graciously wrote the foreword for the book. So I mean, I'll just buy it for the sake of reading the foreword. Yeah, that's good. Okay, yeah, thank you. Take questions.